Welcome to the deep dive. Today, we're really getting into something core to modern data work, how businesses are updating their practices for dealing with huge, fast-moving data sets. Yeah, if you've ever sort of struggled with slow reports or, data that's not quite fresh enough, you'll know what we mean. We're talking about a pretty big shift, moving away from traditional tools like Oracle views and materialized views. Now, they were powerful, no doubt.
Oh, absolutely. Foundational for a long time.
But they can sometimes hit a wall with the sheer amount of data today and that need for instant insights. So, okay, let's unpack this. Our mission today is to explore how tools like PySpark and Delta Lake are stepping up. They're presented as sort of modern, scalable alternatives, turning these big data challenges into hopefully ways to get faster, more robust data processing.
Exactly. And the big picture benefit here, really, is enabling these data pipelines that are not just scalable, which is huge, but also flexible enough for both real-time streams and your classic batch jobs. Plus, with Delta Lake's ACD properties, atomicity, consistency, isolation, durability, you get this near real-time data consistency. And crucially, without the kind of database locking that often slows things down.
Okay.
Which ultimately means faster insights and just way more flexibility for querying over these enormous, constantly changing data sets. It's a real shift in thinking.
That's a powerful why behind it all. So let's ground this a bit. Many of us know Oracle Views pretty well, right? Those virtual tables, like a saved query giving you a specific slice of data.
Mm-hmm.
But when you move into this distributed world with PySpark, how do you actually create those same logical views, those custom perspectives on your data?
Right. So PySpark data frames become your fundamental building blocks here. You can think of them like tables or views, basically, but they're designed from the ground up for distributed computing across many machines.
Okay. Distributed.
Yeah. The key difference, really, is moving from a maybe more rigid database schema to a very flexible, code-driven way of representing data that's built for parallel processing. It fundamentally changes how fast you can iterate.
Right. Code for parallel processing. Okay, let's get practical. Say I'm doing basic SQL stuff like select col1, col2, or select where col2 0. How does that translate?
It translates pretty directly, actually. Selecting columns, picking out what you need, that's just df.select col1, col2 in PySpark.
Simple enough.
And filtering rows like your where clause, that maps nicely to df.filter, df.tilde 0. The syntax is different, obviously, but the core idea is the same, just operating across a cluster.
Okay. And what about combining data sets? SQL union for stacking results, or maybe minus to see what's different between two sets? Those are common view techniques.
Yep, PySpark handles those too. For union, you can easily merge rows from two data frames, say df1.union, df2. You can add .distinct if you only want unique rows, just like union often implies. And for set differences, like equals minus or exceptive. PySpark has subtract. So df1.subtract df2 gives you rows in df1 that aren't in df2. It's all about applying those set operations, but on distributed data.
Makes sense. And joins. That's probably the most common way views bring data together. Customer to orders, products to categories, one-to-one, one-to-many, outer joins, even those tricky many-to-many ones with bridge tables.
PySpark's join capabilities are really robust. You just use df1.join, df2, and specify your join keys like df1.id equals df2.id, and the type inner, left outer, right outer, full outer.
Okay.
It handles all those scenarios. You can even chain joins together for more complex relationships like navigating through bridge tables. It's very flexible for integrating different data sets.
So we can select, filter, combine, join, all the structural stuff. But views often calculate things too. How do we handle calculated columns like in SQL, select col1, col2 plus col3 as cal-col?
Yeah, transformations. PySpark makes that pretty easy with column. So your example would be something like df.withColumn. Calcol, df.cl2 plus df.cl3.
With column. Got it.
Yeah, and you can use all sorts of functions in there, arithmetic, string manipulation, date functions, even things like coalesce to handle nulls. Very powerful for enriching data on the fly.
Okay, and the last common view type, grouped views. Aggregating data, like finding the max sales per state using groupie by Y and max, super common for summaries.
Absolutely. This maps directly to PySpark's groupie and ag function. So you do something like df.groupby, statecode.ag, f.max, salesmt.alias, maxLsamp.
Group B and ag.
Exactly. You group by one or more columns and then apply aggregate functions like max, min, sum, average, count, whatever you need. So yeah, all those standard SQL view operations, they have clear, scalable counterparts in PySpark.
Okay, that covers standard views, the logical ones. But here's where it gets really interesting, I think. Oracle also has materialized views, physical things. They pre-calculate results to make queries faster. What about those?
Right. And this is where Delta Lake really becomes essential, working alongside PySpark. Delta Lake's features, especially its AC transactions and its ability to handle upserts, sometimes through streaming. These are the key enablers. They let you replicate and often improve upon what Oracle MVs do.
Okay, so just to level set for everyone, materialized views, MVs in Oracle, are basically physical tables. They store the pre-computed result of a query, great for speeding up reports or complex aggregations.
Exactly.
And there are generally two main flavors: complete refresh, where the whole thing gets rebuilt from scratch, and incremental or fast refresh, where only the changes get applied.
Precisely. And what's fascinating, like you said, is how PySpark and Delta Lake tackle these, often with, frankly, more flexibility and definitely more scalability than the traditional Oracle approach, especially at massive scale.
Yeah.
This isn't just a technical detail. It means businesses might be able to get near real-time insights from huge, evolving data sets without the system grinding to a halt during refreshes. That's potentially huge for faster decision-making.
That sounds like music to the ears of anyone who's waited for those overnight batch jobs. Okay, let's start with the complete refresh. In Oracle, you might have create materialized view, refresh on commit, or maybe on a schedule. It's a full rebuild.
Right. So in the PySpark Delta Lake world, there isn't that exact refresh on commit mechanism tied directly to database transactions.
Gosh, no magic button.
No magic button tied to the source commit, exactly.
Yeah.
But you achieve the same outcome quite simply. You load your source data using PySpark, do all your necessary aggregations or transformations, and then you write the resulting data frame to a Delta table using mode overwrite.
Ah, overwrite. So you just replace the whole thing.
Exactly. df.write.format delta.mode overwrite.save target path. You're essentially saying, here's the new complete result, wipe out the old one. It achieves that full refresh goal.
But the on-commit part, or even just periodic refresh, that's not automatic then. You have to trigger that overwrite somehow.
Correct. It's not automatic based on source changes. You simulate it through scheduling. You set up a job using tools like the Databricks job scheduler or Apache Airflow, maybe even just a basic cron script if it's simple.
So you control the trigger.
You control the trigger and the frequency. This actually gives you a lot of flexibility. And after the overwrite finishes, you can optionally cache the Delta table in Spark's memory, mvdf.cache. That can simulate the fast query performance you'd expect after an MV refresh.
Okay, that makes sense for the full rebuild. Simulate it with a scheduled overwrite. But often the real power, or maybe the complexity of MVs in Oracle, is that refresh fast option, only applying the changes. How do we replicate that incremental update?
Ah, yes. The incremental magic. This is where Delta Lake's merge command is the star of the show. Merge. It's designed specifically for these kinds of upsert operations, update existing rows, or insert new ones. You often use this in conjunction with change data capture, CDC data coming from your source systems. Or you can process streaming data directly and perform merges on each microbatch. Think of merge like intelligently updating your target table based on incoming changes.
Okay, walk me through that conceptually. How would the PySpark code look, roughly, for simulating an incremental MV?
Sure. Let's imagine you have sales data streaming in, maybe from Kafka. Step 1, define your streaming source. You'd use Spark structured streaming, say spark.readstream, to connect to Kafka, subscribe to the sales topic, and load the incoming messages, probably parsing them from JSON or Avro.
Right, get the stream going.
Step 2, aggregate within the microbatch. So as each small batch of new sales data arrives, you'd apply your aggregation logic, maybe group by proted, timei.ag, some amount sold, to get the latest sales totals for each product in that batch.
Okay, summarize the changes.
Exactly. Step 3, define the merge. This is the core bit. You use the Delta Lake Delta Table API. You point to your target Delta table, your MV, and call .merge. Inside the merge, you specify the source, your aggregated microbatch, and a condition to match rows, like target.proted and target.time equals source.timeid.
So find matching rows based on keys.
Precisely. Then you define actions. A match update, what to do if a matching row exists in the target table, or G, update the $sales column. And when not matched, insert what to do if it's a new product time combination. G, insert the new row.
Update or insert, the classic upsert.
Exactly. Step 4, write the stream using forgebatch. You wrap that merge logic inside a function and pass it to writestream.forgebatch. This tells Spark to execute your merge function on the output of each microbatch of the streaming query.
Ah, forward batch applies the merge logic repeatedly.
Yes. So as new data flows in, it's aggregated and then merged into the target delta table, keeping your materialized view continuously updated in near real time with just the changes.
Okay, so recapping that, the materialized view concept, that becomes a delta table that you can perform upserts on.
Right.
The incremental refresh, that's handled by the merge operation, often used with forcratch in a streaming context.
Hmm.
And the fast refresh speed comes from these frequent small microbatch updates instead of big, slow, full refreshes. That feels like a really different way of achieving the same goal. So, what does this all mean for you, our listener? How does this impact things?
Well, fundamentally, it means you gain scalability and flexibility that can be really hard to achieve with traditional MVs,
Mm.
especially when you're dealing with truly massive data sets like petabyte scale. But it's important to understand the nuances too.
Okay, what are the catches or differences?
One example is oracles with check option. This enforces constraints directly on the view during inserts or updates. So the database guarantees that any data going through the view still meets its criteria.
Right, built-in data integrity for the view.
Yeah. PySpark and Delta Lake don't have a direct declarative equivalent for that on the view itself. Instead, you typically build those checks and validations into your data pipeline logic. You write code to ensure data quality before you write it to the Delta table.
So the responsibility shifts from the database object to the pipeline code.
Exactly. It shifts data governance slightly. It requires more explicit handling in your pipeline code or using separate data quality tools. Another point to reiterate, that refresh on commit idea from Oracle MVs. It's just not there automatically in Databricks or PySpark based on source commits.
Yeah.
Your refreshes, whether full overwrites or incremental merges, have to be explicitly scheduled or triggered by your job orchestrator or upstream processes.
You use a build the trigger mechanism.
You have to build it, yes. And one last practical point.
Yeah.
Partitioning. For large delta tables acting as MVs, partitioning is usually critical. Partitioning by date or region or product category, whatever makes sense for your queries. It drastically speeds up both the refresh process, the merge or overwrite only touches relevant partitions, and subsequent queries against the table.
Don't forget partitioning for performance. Good tip.
Definitely. So if we sort of zoom out and connect this to the bigger picture, the main takeaway is that PySpark combined with Delta Lake gives you the functional capabilities of views and materialized views. You get that logical abstraction, you get pre-computation, but you get it using distributed computing with strong consistency guarantees from ACD transactions, all on scalable cloud storage. While specific Oracle features like auto refresh or the check option aren't mirrored directly, you simulate them effectively through scheduling, orchestration, and building constraints into your pipelines. It's a more programmatic approach, perhaps, but ultimately very powerful and scalable.
That's been a really insightful journey, tracing the path from those familiar Oracle views to this more modern, scalable world of PySpark and Delta Lake. It really underscores the value, I think, in rethinking data architecture for today's needs, faster insights, bigger data.
Absolutely. And maybe a final thought to leave you with. This shift from Oracle-centric MV thinking to PySpark Delta Lake processing, it's more than just swapping out technologies. It really is a fundamental change in how you engineer data consistency, how you think about real-time versus batch, how you manage data pipelines. So consider what implications this shift might have for your team's skills. What about your organizational structure? Does it change how you think about data ownership? And looking ahead, how might embracing this data lake-centric approach unlock even more innovation? Maybe entirely new analytics or business capabilities that just weren't feasible before. Something to think about.